Okay, welcome to the Institute on this one. I actually kind of like this problem because it's dealing with inclines, it's dealing with friction, but it's actually kind of almost a real world situation. So it's set up as you testify as an expert witness. So this is question number 10 because you have the vast knowledge of physics. So that's exactly what I'm thinking in terms of this. But the idea is car A here was traveling along. They didn't realize that car B was stopped, and so they hit their brakes, they slid into the back. So basically they're going to go bam right into the back of them. We're trying to figure out what speed they were going when they hit them. Why would you care about this? Why would you need to do this? How would you calculate this? All that lovely stuff. So the reason why you can actually calculate this is because police officers, accident investigation people, are going to actually want to figure out whether they were speeding or not. Did they keep a true like distance? That type of stuff. And you can do this with just physics. So that's exactly what we're going to do. So one of the things you notice, we've got things like distance. Oops, let's get my pen back. We've got things like distance and velocities and things like that. And we're really trying to find a VF. That's my ultimate goal. So the way we're going to eventually find this, since this distance, I know it's not actually an X, but we're going to think of this as kind of an X that they're traveling. So it's a displacement along the incline. So I know it's not in the X direction, it's not in the Y direction, it's kind of somewhere in between, but since all the motion is parallel to the incline, that's what we're going to use. So eventually, we're going to be using the fact that VF squared equals VI squared plus 2AX. We know VI, that's the 18. We know X, that's the 24. We don't know A, and we're going to try to find VF. Now, I'm going to do one extra little thing. I'm going to get rid of this little square up here, and I'm going to basically put a giant square root around everything. So my main goal here is I need to find the acceleration of this car. This is similar to what we were doing with our lab, our acceleration on an incline lab. So that's exactly what we've got going on here. If I draw a free body diagram for car A here, I have a perpendicular force, I have a parallel force, I have a normal force, and the normal force and the perpendicular force are going to be the same. And then they lock up the brakes and they slide, so they have friction acting. The friction is trying to oppose this motion. Now, basically what happens, and it's going to be kinetic friction, what's happening is friction is smaller than their parallel force, so therefore actually, friction is going to be larger than their parallel force, so it's going to actually slow them down. My hope is they're going to actually have a negative acceleration. So I'm going to redraw this. I should actually draw this so that it is larger than the parallel force. So I have some other things. I know the angle. We have measured the coefficient of kinetic friction to be 0.3, so we have all that. This is what we did in the lab, but I'm just going to go through the process again, just kind of as a reminder. So the acceleration of car A would be the net force on car A over the mass of car A. Now, if you look at the problem, we actually don't know the mass of the car. And there's a reason why, because when we calculate this, the net force on car A, we have a parallel force that's moving toward that. So that's actually going to be in the direction of our motion. And then we have friction acting in the opposite direction. So that's the net force along here, because the normal force and the perpendicular force are just going to cancel each other. And then that is divided by the mass of car A. Now when I plug in my lovely equations, we know how to find the parallel force. The parallel force is going to be the mass of car A times gravity times the sine of theta. And then when I calculate the kinetic friction, it's going to be the coefficient of kinetic friction. Technically, it would be times the normal force. But the nice thing is the normal force just equals my perpendicular force. So I can replace that with how we find the perpendicular force, which is mg times cosine of theta. And then divide the whole thing by the mass. Actually, this would be mass A here. and then just divide the whole thing by the mass A. The nice thing is the mass A is going to cancel from everything. So we can get rid of it everywhere we see mass A. Bye-bye mass A, bye-bye mass A, bye-bye mass A. And what we're left with is this g sine theta minus mu k g cosine theta. And that is your acceleration for the car. So we can calculate the acceleration because we know the angle, it's at 12 degrees, we know gravity, we know mu k. Now, I'm hoping that A should actually be a negative answer because they have greater friction than parallel force, so therefore they should be slowing down. And when we put it into the equation up here, we're going to put it in as a negative number. So it's actually VI squared, it's 18 squared plus 2 times a negative number times a positive 24, and then we'll square root it. It should be positive underneath there, and then we'll find VF, and that'll be how fast it would go once it has slid 24 meters, and basically how fast it's going to hit car B. So this is kind of a neat little equation. I'm going to add this to the equation wall and suggest that we actually grab it because we're going to use it for our lab. We're going to use it for actually one of the questions on the test. So hope you enjoyed.